Here is a very important family of functions. It's called the family of normal distributions. Normal distributions. Bell-shaped curves, like this. See my finger there? These functions are used all the time in probability and statistics. We even have a class called probability and statistics. We use these functions all the time. They are super useful, not only in class, but also on the job. Statisticians, professional statisticians use these functions all the time. I'm going to go ahead and use subscript notation. F sub mu comma sigma. That's the Greek letter mu, and I just love that that's called a mu because it kind of looks like an M and it kind of looks like a U. What else would we call it but mu? Isn't that great? Well, I mean, the Greeks originated that. Probably more likely our letter M and U came from this. And that's a Greek lowercase letter sigma. These numbers stand for what's called the mean and standard deviation, which I'll just abbreviate, standard deviation, STD, DEV is what's that abbreviation, of a normal distribution. I'm not saying what those are at the moment. What's the formula for this? See if I can remember it. I believe it's 1 over square root of 2 pi times sigma times e to the negative x minus mu quantity squared over 2 sigma squared. Whoa, that's kind of complicated. All right, let's get this into Mathematica and just spend some time experimenting with it and doing calculus with it. For the families of functions portions of today's class, we're just going to use technology to save some time. But I do want you to believe you could do it by hand if you had to. So I'm going to enter this as a function. And I'm even going to use a subscript in Mathematica on this writing assistant palette over here. There's a subscript button right here. I can press it. And you see a subscript shows up. I'm going to put the function name right here, tab down here, and put mu. I can make a mu by doing escape M escape. Hey, and there's a mu. Fun, fun, fun. Escape M escape. You don't need to know this, but I'm just showing you for fun. Comma, a sigma is escape S escape. There's a little sigma. I'm using underscores because I'm first defining the function. Once the function is defined, then I don't use the underscores anymore. This formula is 1 over square root of 2 pi. I can make a pi by going to escape P escape times sigma times E has got to be a capital E in Mathematica to the negative x minus mu squared over 2 sigma squared. This will get this normal distribution plugged into Mathematica. Before we do any calculus, let's make graphs of these things. I can put this in a plot. Don't use underscores anymore. Like that. Say x goes from -5 to 5, and let me pick a plot range in the y direction of, say, 0 to 1, and let's make it nice and thick, say, so we see it clearly. But there is a problem with this as is, in that if I enter this, nothing's going to happen. Why did nothing happen? Because Mathematica says, hey, I don't know what mu and sigma are. So I could plug in numbers for mu and sigma. In fact, I could just do it right now, quick, like 0 and 1, for example. And then I would get a graph, maybe too thick. How about this? That's better. But what's more interesting, as I was trying to emphasize in class on Wednesday, is what happens as mu and sigma change. So I want them back in there And to allow myself to change them, I put this thing inside something called manipulate. Don't worry too much about the syntax here. This syntax is going to let mu vary from -4 to 4, say, starting at 0. And this syntax is going to let sigma vary from, say, 0.01 to 10, starting at 1. So here what I have is the case where mu is 0 and sigma is 1. Notice this bell-shaped curve has an axis of symmetry, that is the y-axis there. It's an even function. It's centered on 0. That's the value of mu here. The mean is 0. That's like an average. About half the data, so to speak, is to the right of 0, and half the data is to the left. What do we mean by data? I'm imagining data that this is modeling as what's called the density curve. The fact that the graph is highest close to 0 means most of the data is close to 0, and about half above 0 and about half below 0. The graph gets lower as you move away from 0. So there are very few data points that are far away from 0. If they are far away from 0, relatively speaking, like 3 or 4, they're called outliers. This is related to statistics. Mu really is the mean. It really is the center of this. If I change mu, I change where the center is. Here mu is 2.12. Now the peak is above 2.12. Hey, mu must be a critical point that gives a maximum. And the graph's concave down near the value of mu. I can use negative mu's as well. And sigma, it's called the standard deviation, measures the spread in the distribution. Trying to make that exactly 0, but not having success. All right, it's really close to 0. I made sigma 1 here. What does that represent in this picture? It represents the horizontal distance between mu and the inflection points. The inflection points are at plus or minus 1 here. At +1, which is right about there, that point right about there is an inflection point. You can see the graph changes from concave down to concave up right about there. And over here, there's an inflection point. The graph changes from concave up to concave down right about there. If I increase sigma, the graph widens. The inflection points move away from 0. The standard deviation is bigger. And if I decrease sigma, make it pretty small, then the graph gets tall and skinny. The inflection points are moving towards 0. Why does the graph have to get taller and skinnier? Turns out, to be a valid normal distribution for probability and statistics, you need the total area under this graph to be exactly 1, no matter what mu and sigma are. It's this crazy formula that guarantees that happens. That's related to integral calculus. Integrals are about finding areas. But to verify that you get an area of 1, no matter what mu and sigma are, is actually pretty complicated. You actually need multivariable calculus and something called polar coordinates. We will not go into that. If you take multivariable calculus, maybe that will be a topic for you. But what we can do is we can think about what we can do in single variable calculus. We can take the derivatives. Let's have Mathematica do it. Mathematica, what is f sub mu sigma prime of x? There it is. Use it to find the critical points. You should believe you could do that by hand, by the way. Mu and sigma are constants. X is the variable. You're differentiating with respect to x. You do need the chain rule because you got a negative x minus mu squared there. Although it's a trivial use of the chain rule because you get the derivative of x minus mu is 1. It's worth being thought about anyway. You should verify you end up getting this. That's something you should maybe even do after class. Verify that. Do notice this is going to be 0 when the top is 0. And the only way that happens is if x equals mu. Because e to a power is never ever 0. So yes, you have your one critical point is when x equals mu. That's where the peak of the graph is. That's where the maximum is. Slope is 0 there. And it is a maximum. This changes sign. from positive to negative as x increases through mu. When x is less than mu, this quantity is negative, but because of the negative sign here in front, the entire quantity is positive. And what's the second derivative? I can copy and paste this and add an extra prime in there. Well, it's a little bit more complicated. If I put this inside simplify, well, it's a little bit better. The inflection points would be where the second derivative changes 0. That must be where this thing is 0. It's a quadratic in x. You could use the quadratic formula. Will Mathematica solve it as well? I believe so. If I just copy and paste this down here, set it equal to 0 with double equal signs. You got to use double equal signs when you use solve. Solve for x and square brackets. Yeah, x is mu plus or minus sigma. The inflection points are sigma units away from mu. Wow. You should believe, and maybe you should even do after class this by hand. This is a very, very important example of a family of functions. Your problems were technically simpler than this, though you had to do them by hand. Something you should work at handling. If you felt like you were having trouble with families of functions, I did also have the extra videos that I got more examples that are simpler than this. But I wanted to illustrate this as an important example that's got lots of applications. By the way, to confirm that the area under the graph is 1, no matter what mu and sigma are, I think Mathematica can do that. There is an integral symbol on this palette. If I can find it, if I can move the palette here. Let's move this thing. Here we go, right here. If I integrate from minus infinity to infinity, this function without double primes, I think Mathematica is good enough to say the answer is 1. It's thinking. Okay, well, certainly if I plug in numbers for mu and sigma, it will say 1. It's usually good enough to figure this kind of thing out, but maybe it's having trouble. Okay, I'm going to abort the evaluation. Certainly if I plug in any particular numbers for mu and sigma, like 1 and 2, the answer is 1. If I plug in another set of numbers like 10 and 17, the answer is still 1. No matter what numbers you plug in, the area under the curve is 1. That's a symbolic way of saying it. And that's why the curve has to get higher as it gets skinnier and lower as it gets wider, so that the area is always 1. Though it is a bit mysterious, it's an area that goes on forever and ever, yet somehow it's finite. Really? Yeah, no. Blow your mind, okay?